Hi, I am Wong from Market 20. This is a video presentation for my IAP Exhibition project, Deep Learning with Fpga on breast cancer classification. So, why did I perform this project? The goal is to solve two problems: the inaccuracy of radiologist diagnosis that can be affected by external factors, and second, the classification process takes time, even with a deep learning model. Hence, this project aims to design an intelligent, deep learning-based system that can efficiently perform medical imaging screening to detect and diagnose the type of breast cancer, and the latter, to accelerate the deep learning inference computation using an FPGA. The design system aims to dominate small and large medical healthcare facilities with computerized tomography scanning equipment to substitute the needs of experienced radiologists with an AI-based machine in breast cancer diagnosis. Besides, saying for deployment on large healthcare facilities, such as a hospital, the FPGA can be plugged into a server to allow the deep learning model for various diagnoses to be loaded into the FPGA. So compared to the traditional radiologist that takes hours to days for diagnosis results, using the FPGA, the diagnosis result can be said to be retrieved by the time the patient finishes the addressing. Furthermore, it takes only an FPGA and a well-trained deep learning model to replace all the radiologists. Contribution-wise, the designed deep learning model achieves a comparable performance of above 94% of accuracy to the SOTA studies. This means that the model is capable of performing a very accurate classification on the given breast cancer images while having a fast computation speed, utilizing the FPGA as an accelerator. In short, this saves human life but greatly reduces the diagnosis time. With a wider implementation, the traditional radiologists could have been fully replaced with the proposed accurate and fast model on an FPGA. The inference with an FPGA is designed to work in two ways: a traditional script submission mode or an interactive mode with GUI. The fast inference utilizes the Mustang F100 accelerator card with Intel Array 10 GX 1150 FPGA to speed up the inference process. The GUI allows for simple one-click deployment and classification. The result returns contain all necessary information, including the image path containing the patient's ID, classification result, benign or malignant, and the inference time in milliseconds. In terms of inference time, the FPGA achieves a significant improvement from the CPUs. Although the GPU achieves a comparable inference time with the FPGA, the GPU has drawbacks for real-time deployment, which will be discussed in the following section. The fast inference of a vision processing unit (VPU) is expected as they are designed for acceleration applications. For parallel benchmarking applications, batch size as small as 1 is implemented to mimic single real-time inference. A batch size of 8 is to show how well each device performs on batch processing. Investigating the comparable performance of GPU and FPGA, FPGA greatly surpassed the GPU on parallel processing. Not to mention, it induces the least latency on deployment. Even with the VPUs, the FPGA achieves a far better throughput to latency trade-off. The same applies to batch processing. The FPGA is capable of producing a high throughput while inducing the least latency on batch processing applications, and the low latency greatly surpassed the VPUs. The last section here provides an overview of the time required for swapping in a deep learning model into the FPGA. This section provides an insight into the time required for real-world deployment applications mentioned previously. Comparing all the deployment platforms, the reading time is comparable. However, the network loading time differs on different devices, but the differences is in mere milliseconds. Thus, this concludes that the swapping time on an FPGA is minimal and is feasible for deployment. Right, so with this, I conclude my presentation. Thank you and goodbye.